Okay, welcome to part 2 of chapter 16. We have begun discussing some innate immunity and some factors that are involved in innate immunity. We did part 1, and now I'm ready to begin part 2 as well. So this again is a 3-part series, and this will be part 2, and I'll then upload part 3 later. So the next topic we're going to look at is immunity. And these are just some basic ideas and some chemical factors that are involved in immunity, mainly looking at proteins and their role and their function in the cell. And you'll hear so often that these compounds are proteins, which makes sense because, and this is kind of an aside, but our genetic material, our DNA, it's a code for the construction, the building of proteins, and so it makes sense that all of these defensive compounds are protein based, if not entirely proteins altogether, because this is our code of life. This is what DNA codes for. So we'll be looking at many of these different types of proteins that are involved in immunity and in regulating immunity as well. So we'll look first of all at TLRs. TLR stands for toll-like receptors. And toll-like receptors kind of has a funny name. It comes from a gene that was first discovered in Drosophila, the fruit fly, and it's called the toll gene. And the toll gene produces this protein, and this protein that the toll gene produces scientists discovered is similar, or I should say it the other way around. The toll-like receptors are proteins that are very similar to the protein that was produced by the toll gene. But you don't care about that. Let's just talk about toll-like receptors. So these are protein receptors in the cell membranes of defensive cells. They attach to various parts of the microbes. They activate innate immunity. And so these are proteins that will, when they recognize that this is an antigen, that this is a foreign body, that this is a foreign protein, or that's within a system of the body, they will begin initiating innate immunity and some of the systems that are involved with that. So once they breach these physical barriers, for example, our skin or our mucosa of our intestinal tract, they're recognized by TLRs, and then that begins a cascade of events that follows thereafter, all involved in regulating and beginning innate immunity. Cytokines are another group of proteins that are released from defensive cells, and so this is one of the first steps that happens. So once the toll-like receptors are activated, one of the first things that happens is that our immune cells will begin to release these proteins called cytokines. Cytokines regulate the intensity and duration of the immune response, and so our body has to continually be monitoring this and regulating this. This is kind of like a term that's used as immunomodulatory, and cytokines are involved in that. So we get a small cut, say, for example, and bacteria enter. Well, this is not a big deal, and so the body then responds, at least it's supposed to, and in some cases it doesn't, and that's another topic altogether, but the tissue responds in a certain way, like this is just a small scratch. There are only a few bacteria, so let's not make a big deal about this. And so the cytokines are there saying, let's not make a big deal about this. However, there are instances with allergic responses, or in response to some toxins that are produced by bacteria, which are called superantigens. It forces the immune cells to release a slew of cytokines, and that's called a cytokine storm. Staphylococcal food intoxication, we call it food poisoning. That's one example of that, or toxic shock syndrome, cytokine storms. This is what COVID does, COVID-19, the SARS-CoV-2. What we're dealing with right now, it causes a cytokine storm, and it causes severe inflammation, especially within the respiratory tract and cells within the respiratory tract. So therefore, it causes a great amount and a great release of these cytokines, which we don't want. under normal circumstances. So anyway, that's a topic that is to be discussed later, we'll say. But just for now, cytokines, proteins that are there to regulate the intensity and duration of the response, and interestingly, it's present in the colostrum. So whenever an infant is nursed, the child then receives these beneficial cytokines through nursing, through the colostrum as well. Just an interesting fact. Referring to the normal microbiota, well, what do they do for us in terms of helping us with our immunity? Well, there's this topic called microbial antagonism. This would be, what are the normal microbiota doing? I mean, we're colonized by billions of them. And so what effect are they having? Well, first of all, in terms of their symbiotic relationship with us, they're considered to be commensals, meaning they receive benefit, we receive neither benefit nor harm from them. But one way, and it's kind of indirect, it seems a bit like mutualism, but it's not, because we're not getting a direct benefit from them. But indirectly, we're benefiting because they're competing with pathogens for nutrients. So we are prime real estate, and the bacteria want to reside on us. They want to be there to receive nutrients and a place to live from us, and so they're going to compete for this real estate that's on our skin or in our intestinal tract or wherever. And so, in order to protect their turf, so to speak, they produce substances that are harmful to pathogens and ones that's going to keep them from colonizing us. So they're helpful in that way to us. Not necessary, as we found, but they can be helpful in that way in preventing the colonization of pathogens on our skin or elsewhere in our body where normal microbiota can be found. They also alter the environmental conditions. So from the production of their waste products or some chemical compound that they produce in response to competing microbes, they will change the pH, the oxygen availability, the salinity, and so forth in order to make the environment best suited for them and not suited for their competitors. So microbial antagonism. Now we'll look at white blood cells. White blood cells, there's many of them, and we will look at a few of them. Neutrophils, basophils, eosinophils, dendritic cells, monocytes, and lymphocytes. What I want you to notice, and we will at least with the first three, the neutrophils, the basophils, and the eosinophils, you're going to notice some similarities between them when we look at them a little more in depth here in a minute. But the neutrophils, phagocytic and motile, they're moving around, consuming microbes, consuming pathogens, and during the initial stages of an infection, they are very active. So they're cleaning things up. They're phagocytic cells, and they're very good at ingesting these pathogens and any antigens that may enter. Basophils produce histamine. Histamine then is involved in the inflammatory response. So basophils, when we talk about inflammation, they play a key role in the process of inflammation. Eosinophils are toxic to parasites. They do carry out some phagocytosis. But when parasitic worms, for example, or flukes get into our bodies, eosinophils their numbers spike as a result of a parasitic infection, and they release compounds, proteins, and enzymes that are very toxic to parasites. Dendritic cells. Dendritic cells are they have long extensions, hence the name dendritic. That's their the adjective or the term dendritic refers to having many branches. So these long extensions greatly increase the surface area of these cells, and it makes them capable of capturing cells, phagocytizing them. They also initiate specific immunity. So in some cases, they don't phagocytize their prey, so to speak. They are in a class of cells called antigen-presenting cells that present antigens to lymph nodes. And we'll talk about that in Chapter 17 with specific immunity. We'll look at two different types of antigen-presenting cells. One of them being dendritic cells, and the other being activated macrophages. Monocytes, they are phagocytic when they become macrophages, and they are just the killers of the cell. They literally will eat themselves to death, and they can consume thousands of bacterial cells, and that's what they do. That is their role, and they are very good at it. Lymphocytes are involved in specific immunity, and the two big lymphocytes are T cells and B cells, or T lymphocytes and B lymphocytes, as they're known as well, and natural killer cells as well, which we'll talk a little bit about in this chapter, and then also in specific immunity as well. Natural killer cells kind of are in that. What do I say? They are active in innate immunity, but they're also active in more active, I should say, in specific immunity as well. Wandering macrophages, they roam tissues throughout the body, and so they're going from one location to another, and we have fixed macrophages as well that remain in those areas of the body that continually or readily access portals through which antigens and pathogens can get into the body. And so we have those macrophages there all the time because we need them there all the time because they're subject to an onslaught of junk, basically, pathogens and antigens and toxins. The wandering macrophages are just out wandering through tissues throughout the body, looking for and then engulfing and phagocytizing any pathogens. This just gives you an idea of the percentages of each of the white blood cells in a sample of 100 white blood cells. As you can see, neutrophils comprise a vast majority of them, followed by the lymphocytes, 20 to 25%, and the monocytes, the eosinophils, and the basophils, which produce only 0.5 to 1%. This is out of 100 white blood cells. So neutrophils, definitely the most numerous of the white blood cells that are circulating within our circulatory system. Perforin, protein, you'll see these are proteins or enzymes as well, formed by natural killer cells, and we love that name. You'll see many presentations, and whoever is giving the presentation will say, I love the name natural killer. It's just the best name for them. For one scientist, they got it right. When they named the cell, they gave it an awesome name. I don't know who was the naming of that cell, Chuck Norris or Arnold Schwarzenegger or something, but natural killer, that they nailed it on that one. So these are cells that are going around and they are bonding with other cells because of the receptors that they recognize on these foreign cells. They then release these proteins which perforate their plasma membranes, and then the cells will burst, as we call cytolysis. Granzymes are protein digesting enzymes formed by these natural killer cells as well. This causes cellular destruction, which will release microbes, which can then be phagocytized. So say a cell is filling up with viruses, for example, and the viruses are multiplying and dividing within the cell and trying to create more and more of these viruses within them. Well, natural killer cells can cause the bursting of our cells, which will then release all these viral particles, and then they can be phagocytized, and these particles never have a chance to then mature and then become infectious viruses that then can travel through the body and infect other cells. So this would be the big benefit of that, the purpose of granzymes. T and B cells are non-phagocytic, so they do not break cells down. They don't break down the pathogens. They're non-phagocytic, but they're key to specific immunity through their production of antibodies and other immune system chemicals, which we'll talk about in chapter 17 later. So let's look at phagocytosis, the actual process of it. Well, we have the word phago, which means to eat, and cyte, which refers to a cell. So an eating cell. A phagocyte then is a cell that eats and eats and eats, and that's its role, that's its job. Ingestion of microbes or particles by a cell. And so these phagocytes are carrying out this process throughout the body, consuming these pathogens and getting rid of them. Phagocytes can be activated by the bacterial cell components and or cytokines secreted by other phagocytes. So these cytokines will attract other phagocytes to this area where the pathogens happen to be, and that just increases the number of the phagocytes. And so these guys they're responding to chemical signals. And they have to. If they were just going out and eating whenever they were hungry, so to speak, that would be awful. That would be so destructive to us. So they're only responding to chemical signals that are given to them by other cells. Whether they're other phagocytes or whether they're T cells or natural killer cells, they are activated by these other proteins that are floating around within the circulatory system and the lymphatic system. And there are two types, as I mentioned before, fixed and wandering. Fixed, staying in one location; wandering, moving around through the lymphatic and circulatory systems. So this diagram here just shows you what happens in the process of phagocytosis, so that you can see it graphically. And I always say pictures are so helpful. As we learned in kindergarten and still here in college, they're still quite helpful for us, aren't they? So what happens is you ingest this microbe or other particles. You can see in the upper left, this nondescript brown thing goes into the macrophage and forms what's called a phagosome. So what envelops that microbe is actually the part of the cell membrane of the phagocyte. Then, once inside the cell, the lysosome meets up with the phagosome, and now we have what's called a phagolysosome. And within the lysosome, that's where the digestive enzymes are. So the macrophage itself, the cell membrane, that becomes the vehicle for bringing in these pathogens, because they have all the cell membrane receptors that identify this as an intruder. The lysosome contains all the lytic enzymes, hydrolytic enzymes that will break down these, in this case, this microbe, this bacterium, whatever it is, into these little bits and pieces that we call residual bodies. And then step number 7, we have exocytosis, discharging the waste materials back into the circulation. So now we have a neutralized entity, whatever it happens to be. In this case, we'll say it's a bacterium, which can not release its toxins, which can then not cause sickness, illness, and infection. So the steps of phagocytosis, I tried to make them simple. So we have chemotaxis, and that just means a movement toward a chemical. You can see the word there, the suffix of that, taxis. Get rid of the S on the end, we have a taxi, and you think of that yellow cab that drives us around. So they're moving towards a chemical, and that's what chemotaxis is. Now, how do phagocytes know to do this? Because they're told to by other compounds, immune system compounds, proteins that are being produced. Step number 2 is adherence, and then which leads then to ingestion. Adherence would be through the cell membrane proteins that are on the surface of the phagocyte, bonding with the proteins of the pathogen, whatever it happens to be, a virus or a bacterial cell. Then ingestion through pseudopods, which means false feet. So these are cytoplasmic extensions that reach out and engulf the pathogen. And then digestion, which takes about 10 to 30 minutes, depending on what type of phagocyte is doing the digestion and what it happens to be digesting as well. So these are the 4 main steps of phagocytosis, kind of more simplified. Now, microbes can evade them, and I want to talk more about this in a later chapter, the chapter on mechanisms of pathogenicity. How do they overcome our defenses? Well, in this specific one, they can evade phagocytosis. Now, what are some ways they can do that? If they inhibit adherence, nothing can happen. So that prevents ingestion. That then obviously prevents digestion as well. So the adherence then, it just slips right off of it. It's kind of like Teflon. It just slides right off of it. And so therefore the phagocyte never has an opportunity then to ingest the microbe. They can kill or lyse phagocytes. So they can even bring about the destruction of the phagocyte itself. They can escape the phagosome, which they don't get locked up within it, and so therefore they are not subjected to the hydrolytic enzymes from the lysosome. They can prevent the fusion of the phagosome and the lysosome. So the bacterial cell is in a phagosome. He kicks back and relaxes and said, well, there's no need for me to worry because I can prevent the fusion of the phagosome and the lysosome. So then it can't be broken down by the hydrolytic enzymes. And they can, some of them, because of the capsules that they produce, for example, they can even survive in the phagolysosome where the enzymes do nothing to the bacterial cell. So these are ways that they can evade or escape phagocytosis and its effects. So looking at inflammation, well, here are of course, the cardinal signs and symptoms of inflammation: redness, pain, heat, swelling, edema. Acute phase proteins are activated, so we get localized and systemic reactions just depending on the extent of the injury, for example, which will bring about the attraction of, say, white blood cells to the area of injury. Vasodilation and increased permeability, so we open up blood vessels, the capillaries open up, and now white blood cells can get out of circulation and get to the area where the injury is occurring, where the bacteria have been lodged, and then start phagocytizing those bacteria. And that relates to margination and emigration of white blood cells and tissue repair as well. We'll look at that graphically later. Some chemicals that are released by the damaged cells. So what leads to this inflammation, this swelling and edema in the puffy tissue that results from an injury? Well, we have these guess what, proteins, surprise, histamine, kinins, prostaglandins, and leukotrienes. So you'll notice in many of them, all of them, they're all involved with vasodilation, increased permeability, in order to get the white blood cells out of circulation. Because if they remain in circulation, what good can they do? So causing vasodilation and increased permeability, the white blood cells can get out, they can phagocytize the bacteria, clean things up, and then lead to tissue repair. So it's a multi-step process that occurs when we do become injured, such as bacteria entering through a knife wound or a scratch or something like that. But as you'll notice in all four of these, as you read through one of their purposes, it's all about vasodilation, increased permeability, assisting the phagocytes getting to the site of the injury or damage that has been done. You can see here that okay, so we have this unfortunate event: bacteria enter the skin on a knife. Ouch! As a result, then the bacteria and the damage to the tissue cause the inflammation, cause the release of histamine, and as we were just looking at, kinins, prostaglandins, and so forth, and that leads to the swelling and puffiness of the tissue. And now, as a result of this vasodilation and increased permeability, we have all of these white blood cells able to get to the site of the damage, where they can leave circulation, as you see the emigration, where the phagocytes are squeezing between endothelial cells, and the margination, where they're sticking to the endothelium, which enables them to get out of circulation. So you can see the neutrophil there in the picture on the top, squeezing out between the cells of the blood vessel, the wall of the blood vessel. And then, of course, we have the scab, which is that protective covering over it, and then the skin or the dermis, the epidermis, starts to regenerate and begins healing itself. So that's it for part 2. This is a good place to stop. For part 2, I'll have part 3 coming up soon, and I hope this part 2 has been helpful to you and has given you a better understanding of what's going on here in our innate immunity and the mechanisms involved with that. So thanks for watching.